Exams, is that what happened? I know that's what's kind of going on. It's cold outside, that was annoying. Right? Getting to the busy time of the semester, I guess is what it is. Anyway, though,
I think that's all he's gonna ask.
we were making our way through the kinetics part here, and we had talked about, the generic expression for a rate law, how to calculate the exponents based off of experimental data, right? Setting up the ratios between the different experiments where you hold things constant and that kind of stuff. And from there, we went to discuss the integrated rate laws, which is our way of starting to calculate what happens to concentrations over a given period of time, right? So the book makes it sound scarier and all these kind of things, but this is really what it comes down to, right? They give us a time, they give us an initial, right? We have to calculate K and just kind of work our way through the calculator, right? We then talked about the special case where if we have a first order reaction, we can talk about half-life and that kind of thing. And maybe I didn't make the point necessarily as salient as I wanted it to, but when we tend to think about half-life, we think about nuclear decay and that kind of thing. But that's not necessarily the only instance where we can discuss half-life, right? Because here we're talking about half-life and we're not really talking about any kind of nuclear decay or that kind of thing, right? So it's just a special circumstance that comes in when given conditions are met, right? First order reaction, that kind of thing. That's all we're really doing. All right, so then we had a series of questions. We were working our way through it. I think we got through part A, and so we'll see if we can get through parts B and C today. Oh, that's why, right? It's the March for Life thing.
Fire drill.
That's fine. I forgot that's what's going on today. That's why people are absent. Yeah, okay. But anyway, so we'll work our way through parts B and C, and then we'll talk a little bit about reaction mechanisms and some of the maybe trickier ideas to kind of work our way through here. But we'll get that wrapped up, and then probably on Monday we'll work through a couple problems as we tend to do at the end of the chapter there, right? I want to give you guys a little bit of extra time today to go work on the quiz and stuff also, right? And remember, there's a quiz. It should be up. 4 or 5 questions in there, something like that. So very good end of the chapter problems. Very typical of what I would expect you guys to be able to work through and do on an exam, right? So make sure that you guys are spending the appropriate time with that. Is all I'm saying. All right, but yeah, what's up?
Is the exam online or like?
We're gonna do it in person as long as we can. Just to it makes life a lot easier for everybody, in my opinion. But we'll see. Yeah, like I said, it's kind of depending, and we have to kind of go with the ebb and flow of things, and but hopefully we can get all done like that.
I'd argue that having the open book online exams makes everything significantly easier than those taking the exam.
Well, I mean, it's there are those side of things, right? Sure, it's always nice to have the security blanket, so to speak, right? The book around. Anyway, so let's get started. Let's get started with prayer, and then we'll continue on here with our words. But Lord, we just thank you yet again for another day and another blessing of that day, Lord, that you've given to us. And we pray that we make the most out of it, Lord. We pray that we can just see you and just hear your call to us today, Lord, just to follow the path that you've set before us in this day that you've made for us, Lord. We just pray to be the good and faithful servants, and that we can follow your calling, Lord, whatever that is. We just pray for the people who are marching for life there, and it's we just pray for those people, Lord. We just pray for an end to abortion in this nation, in this world, Lord. We know that's not something that you want, Lord. We know that's not something that you rejoice in, and we know that if you wanted to, Lord, that you could give us the strength just to change it, Lord. So we just pray for that strength. We pray for that courage. We pray for a voice, and we just pray for our voice to be heard, Lord. We just pray this in your name. Amen. All right. So, let me go close the door here before I give free lessons to the people in the hallway, right? I don't want any of that. part A, and we were making our way to part B, right? So part B was asking for the time for the initial concentration to drop to 1/16, right? With initial value there. Okay? So maybe we just got some space right there. Have at it. You should all have the relevant info up there for what you guys might need. One job to do, man, one job. I'm watching the math happen. It's all good. Part of my job is just to walk around and make you feel nervous. I can tell he's judging us harshly, right? That looks like you got it all right. Yeah. It looks like if you follow through with that, you should get to your answer.
I don't know.
Well, I think you do know. Right, so basically the question is asking, you've got an initial concentration, right?
Yeah.
You've got a concentration that's 1/16 of that, right?
How would you find out much?
So you've got this, right? You've got
Yeah,
that.
okay.
We calculated that, right?
Yeah. Okay.
I know I'm going about this a very stupid way, but my brain isn't functional today.
I'm not gonna get you the answer right.
That's because it does look kind of unfortunate.
Oh, well, actually, hang on, what are you doing? How do you get to that?
I'm just dividing each one by.
Interesting. Okay, so I see what you mean. I was
Yeah.
kind of going out a different way here.
It's not a good method, but it's a method.
Well, if it gets you to the answer consistently every time, right?
Yeah, but it's time consuming as heck.
I think that's true for all of chemistry. Oh, you just, okay, all right, you're good. Sorry, I was waiting, I think you're all playing. No, you just, yeah, you're all good, looks like you'll get there. Awesome. Right? Remember, there are more than one ways to answer this question,
Okay,
right?
so I would know how to do it by just,
Okay, so show me how to do that.
yeah, but I know how to do it by figuring out.
Now the trick is to put on their paper, right?
Or like if number wasn't so simple, I don't know.
So if it was more difficult, you could do it. No, I understand what you're saying, right? It's like you can conceptualize what's going on, but kind of putting that numerically is the
Yeah,
challenge, right?
like if this was like 150.
Sure, sure. Then it'd be different, right? We'd have to approach it in a different way then. But don't worry, I'll probably help you out with that, because I'll show you guys both ways of doing it. So, where'd you get this from? No, I don't think you're that far off, right? So remember, whenever we're starting a problem like this, right, there's always, you got the right equation, right? So that we know this is what we have to use. This is our initial concentration, right? Which we have up there, right, the 0.5, right? So this should be 0.5 here. The A0 is our initial, right, wherever we're starting to look at it. Cool. And then this is our concentration after that amount of time passes, right? And we say 1/16 of our initial concentration. So it's just 0.5 divided by 16. Hmm? Right, yeah. But be careful, right? So this is initial and that's after time passes. Cool. Good. Oh, yeah, already see. You have a question?
Yeah, so like, with this molar,
Mhm.
what would the frequency be?
Does it matter what the units are if you're just dividing something by 16?
Did you really just take your fishing rod and?
If you have 16 oranges, right, and you divide it into 2 parts, there's the parts, right, the units will change.
Questions that we
Lacey, it
Yeah, I
was
just-
2 in the morning and it's
Uh-huh.
freezing cold.
All right,
Yeah, fishing. No one knows.
so let's think about what information we have here, right? We know that whenever we're asked to relate changes in concentration with time, right, we have to use one of those integrated rate laws, right? That's pretty much the only way that we'll be able to calculate that stuff out, right? And our equation is this one here, right? Okay. And so we have an equation, we've got 1, 2, 3, 4 parts to it, right? We've got 4 variables, I should say. And so we should see what information we have. We have a sub 0, right? That's equal to 0.5, right? Moles per liter. T is what we're asked to figure out, right? Calculate T. And so A sub T is equal to, whoops, should be on the outside. A sub T is equal to 0.5 divided by 16, right? Because it says, how much does it take for the initial concentration to get to a 16th of where it started, right? And we have K, right? K we calculated from last time. So 1.733 times 10 to the minus 3, right? Inverse seconds or over seconds. Good? So if we get all this stuff and we plug it into our equation, we should have an answer for it, right? And that's fine, that's a perfectly fine way of doing it. Okay? If you do it that way, you'll get to the right answer, it's great. But we can also think a little bit here, right? Is this the only way that we could answer this problem? Well, let's think about this for just a second while I throw things, right? What does this mean? It's a half-life, right? What does a half-life mean? If I start with 1, After an instance of a half-life, I'll end up with
Half.
a half. Then I start with a half, I have another instance of a half-life, I end up with
A quarter.
a quarter. Right, I start out with a quarter, I have another instance, I end up with,
An eight.
right? You guys get what I'm saying with this? A 16th is a function of a half-life, right? It's a half of a half of a half of a half, right? You guys get what I'm saying with this? So essentially, another way of looking at this is, right, this is a half-life here, right? That equals one of our T1 halves. You guys with me on this? My initial times a half of my initial equals one instance of a half-life, one period of that. Got it? I could take that one half and do another half-life, right? And that would equal, well, I'll do this at the end. Another instance of a half-life, right? I could do it again, just to stop writing everything out, right? To an eighth. That's another T1 half, right? You guys with me on this one? Every half-life halves what I started out with. Got it? So how many total half-lives does it take to get to a 16th of where we started? 4, right? And how much is each half-life? How much is each instance?
400.
400. So what's our answer? 4 times 400 is 1600. If you guys did the equation out the long way, what is your answer? What was your answer? 1600 point maybe something here and there, right? Based on some rounding. Okay. Now understand that this only works when what? We have things each time, right? Because this is a half-life, right? If I ask you for a 15th of the initial concentration, then we would have to approach it in the other way there. Got it? So don't forget what, this is just kind of one of these kind of special instances of how this works out. Makes life a little bit easier. Good? All right. One more. Sorry. Looks like it's gonna be a good day to take a nap in the hammocks out there tonight, so.
Yeah, I have classes and work straight and 6 times
They have some cool stuff up there.
I have some confidence that it was decreased by methods.
Ah,
It's not coming out, it's coming out to a negative number.
Something. Are you forgetting the negative that's out in front there?
No,
Okay.
because it's this minus that, right? And that's gonna be
Okay.
I don't know, sorry.
It's all good.
I have no idea what I'm doing,
Yeah, it looks like it's probably just a little calculator input issue there.
probably, but I don't know how to use a calculator.
Well, you do have to get that issue fixed, right?
Yeah, that's what bit my butt a lot when I was taking the SAT and stuff.
We're gonna shockingly use the exact same formula that we've been doing now for the last, 40-ish minutes up through the last class period. Okay? We're given a sub 0, right? Later, t, again, is our question mark in this case. A sub t is 0.05. And k is still the same one that we had before, right? So what was it, 1.7, yeah, 1.73, right? Good? So if we plug and chug that all in there, you guys will allow me the liberty. I got my time equal to about 1,300 seconds. I think exactly what I figured out was about 13:30 seconds there. Give or take a little bit of rounding here and there. Good? So how scary are these equations?
Pretty, not very.
The natural log's a little bit weird, right? Remembering how to calculate k. If we have the instance of a half-life, remember we have a good way of calculating k based off of that expression of the rate constant for a half-life there. Right, k equals natural log of 2 over the time, right? And once you find out a rate constant, guess what it is? It's a constant, right? For that rate, right? For that reaction. Got it? Good? Would it be useful to practice a couple more of these maybe out of the book? Probably, right? Would it be useful to maybe practice one of the 0th order or the 2nd order rate laws? Integrated rate laws? Probably. Are they going to be handled any differently? Nope. Right? They all have the same basic setup there, right? Initial concentration, concentration after elapsed time, rate constant, and some value, right? Yep.
And that rule is half-life only applies to the first order ones, right? Or
Well, which rule?
that you can,
When we can discuss half-life, yes. Yeah.
okay.
What does K represent again?
It's a rate constant
And so that's always just gonna be the same.
for a specific reaction, yes,
When would it be different?
for a different reaction. Right?
Like one similar, would it be like, say you added a negative to one of the, values, would it change K at all?
Well, you can't have a negative concentration, right?
Okay.
If you have a completely different reaction, then you're gonna have a different rate constant for that.
Okay.
That's all it is. So it's something you're gonna have to calculate or be given for whatever reaction that I'm asking you guys to look at. Okay?
So does the half-life factor into how you solve this problem at all?
Yes, remember that's how we initially got K, right?
Okay.
These are all tied together, but the first thing we did was solve for K for this entire set there, right? Which is the stuff over there on the right hand side. Yeah, what's up?
So in the other reactions, are you just gonna give us K, or
I
like?
could, or I could ask you to calculate in some way also, right? In any case, I have to give you the information to calculate K, right? So I have to either give you the data from, like with the Let me scroll back up here, right? Where was it? Right? So remember when we were working through this, there it is, okay. Right, we were working through this problem here, right? We set up our rate expression, we calculated M and N, right? And then we came back and calculated K after we were done with that, right? So that's another way that we have of calculating K, okay? But there has to be, like, I can't just, there's no way to like memorize rate constant, right? It has to be either given or calculated is what it is.
Hey Doc, I think I'm just really confused on, the stupid whatchamacallit, natural log thing, it's giving me like negative numbers when I solve for when I put in the natural log of like 0.5 or 0.05.
Just factor out the negative.
Just what?
I'll take a look at what's going on here afterwards, but there shouldn't be an issue with that. I think you're just leaving off a negative somewhere is what it is. But I'll take a peek at it. Sounds good? Cool. All right. So there's that. All right, so let's go into the last-ish topic out of this chapter here, and that's the idea of a mechanism. And there's going to be a couple of, how would I say this, concepts that kind of will carry through other parts of chemistry also. And I'll kind of point those out when we get there, right? But just kind of this wall of text here. When we're talking about, a reaction on the individual basis here, right? We could have these unimolecular reactions, we could have bimolecular reactions. Technically, you could have, termolecular, right? So 3 things coming together, reactions, but it's pretty rare, right? By far, the vast majority of steps that happen in chemistry, of reactions that happen in chemistry, are unimolecular and bimolecular. Now, this is kind of a throwaway statement here, but about halfway through OChem 1, we're going to learn exactly where this comes back to bite you in the butt, right? So, I promise it's very, very, very important, but we don't, unfortunately, just the way kind of things are structured, we don't deal with it too much in this class, right? Because we look at mechanisms in this class from a very quantitative perspective, right? We start to ask how much of our concentration is present in these kind of things, right? Whereas in organic chemistry, we say, show me the steps of the mechanism itself, right? And there we have to keep in mind that it's either one thing reacting with itself, so to speak, right? Or 2 things reacting together to make something new. That's kind of the idea here of a unimolecular versus bimolecular reaction, right? But both of these are elementary, right? It's what actually happens at the nanoscale, right? So if we could sit and zoom in and watch the atoms rearranging or moving around, we would see this happening. And there was just for what it's worth, there was a recent paper that was published that they were able to zoom in and actually see a crystal start to form, which doesn't maybe sound that impressive to you guys, but when you're looking at the atomic level of these atoms moving to arrange themselves in specific geometric patterns, it's absolutely fascinating, right? Despite everything that we know today, right, it's still not that easy for us to start to zoom in and see individual molecules or atoms, right? And there's a reason for that, which we learned about in Gen Chem 1 there, right? What's up?
I was basically just gonna ask that, like, how did they record that process?
I'd have to go back and reread it again, like the device that they set up with it, to be honest. I mean, this is something that, is very physics heavy, and it takes me time to digest it, to be honest. It's complex, not really my field, right? It's impressive. I got that sense out of it, but I'd have to go look it up to kind of digest it a little bit more there, I guess is what it is. Anyway, so observed reactions on the macro scale are elementary or complex, but if we're talking about complex, we can basically say these are just a series of elementary steps. Okay, so what in the world does all this mean here, right? If we take the most challenging of mechanisms, we can break it down into individual parts. is all it's really trying to tell you guys, okay? It's eating the elephant, right? How do you eat an elephant?
One bite at a time.
One bite at a time, right? So that's all we're talking about here, okay? So find the individual chunks, and those are going to be either unimolecular or bimolecular. And from that, we can back out a rate equation, or a rate expression, I should say, for these individual reactions themselves, okay? All right, so a couple of important terms just to kind of put together here so we can start to look at some graphical representations of this as we go forward. We have a what's known as a transition state, and the point at the top there probably doesn't mean anything right now, unless you guys have read ahead in the book there. It occurs at the top of the activation barrier. Wow, does it really, huh? Amazing. Okay, so I'll point that out to you guys, right? It'll make a little bit more sense. I'll put this into a different kind of context and simplify it, right? What is important to recognize is that these transition states occur, or they exist for only fractions of a fraction of a fraction of a second, right? Times 10 to the negative 15, if even at that, right? And that's part of the problem that we run into, okay? How can you measure something that only exists for, if we're lucky, times 10 to the 15th seconds, right? The answer is, we can't, right? Or not very easily at all. Now, as technology improves and as computers get faster and all these kind of things, we can start to get a little bit closer to that time scale, right? But we can't even fathom how short an instance of time that is, right? So now we have to measure something to get data and then back out, an equation from it. That's very challenging to do. Falls apart to form products or reactants. Now this is going to get into the next chapter. Yeah, next chapter we're going to get into equilibrium, and so that'll start to make a little bit more sense there, right? Once we're at this transition state, you've got two directions that you can go. Essentially, you can go to the left or to the right, to the reactants or to the products. That's all it's saying there, okay? And then if this is I guess there should be a if statement there. If we're dealing with an exothermic reaction, then the products are at lower energy and the reverse reaction will be slower. If it's endothermic, then it's going to be at higher energy and the reverse reaction is going to be faster, right? So it's just kind of the mirrored statements there, right? And again, I'll put this stuff into a graphical form here in just a minute, and then you guys can maybe see it a little bit easier, okay? So what do I want you guys to know out of this? Well, first of all, I need you guys to be able to understand, or when I say the word transition state, right, just kind of have this stuff in mind. It's in the I have to be careful, I almost used a different term here. The transition state is in between what happens, the reactants and the products of a reaction itself, okay? It's at a specific point. So just for instance, we'll talk about this reaction here for a little bit. We have iodide reacting with methyl bromide, and we make methyl iodide and Br minus there, right? So for this reaction to happen, right, and this is one of the first things you guys learn in organic, how that works. But one thing that we have to pay attention to is that for this to happen, right, that statement there at the bottom has to be true. The iodide has to collide with the methyl bromide with enough energy at the right time, at the right speed, right, at the right location.
Iodide seems rather needy.
Well, every reaction is like this, and that's the whole point. For a reaction to happen, all I'm saying here with this statement is these molecules have to come together, and everything has to be checked. Do you have enough energy? Yes. Are you coming together at the right orientation? Yes. Are you coming together at the right speed? Maybe, right? Are you coming together at the right time? I don't know, right? But if any of these things aren't met, then a reaction can't happen, okay? That's all I'm really saying with this. There are a lot of conditions, so to speak. So here's kind of a visualization of that there on the right-hand side, right? The purple sphere there is the iodide, and the orange sphere with the gray and white stuff there is the methyl bromide. There's different ways that these things can come together, but only one orientation, speed, direction, time will actually lead to this product happening, right? The other ones, they'll just kind of bounce off each other or nothing will happen, right? That's kind of the idea there. Now, in the book, it talks about sterics, right? And we've mentioned that word a little bit here. I wouldn't say I necessarily disagree with the term that they use in the book there with sterics, but I say there's more to it than what they're talking about there, right? They talk about, only a small fraction of the collisions have this orientation. Sure, okay, that's fine. But there's a different, we'll bring out a different idea of sterics as we move forward through chemistry also, right? So, but it's fine for now. All right. So, if we take these ideas and we plot, let me scroll up and get that bottom. Right, okay. So if we take that idea and we plot it out into what's known as a reaction profile diagram, okay? Now, since all of you guys are going to go on to graduate school in chemistry, I'll share this with you guys. So when you actually sit here and computationally analyze a reaction, what you end up making is a three-dimensional plot known as a potential energy surface, okay? And so it's literally a 3D plot of energies based on the orientations and directions of the molecules and where the electrons are and these kind of things, right? Very, very, very pretty, colorful graphs come out of it, right? If I take a two-dimensional slice of that surface, this is what this is looking at here, right? I take something three-dimensional and I just cut a slice out of it, and this is our easiest way of representing this on paper is kind of where it comes from, okay? And I'll show you guys a little bit later just some of these other surfaces that can come out of it, right? So what does this tell us? All right, so important things to recognize. On the left-hand side, that's where we put our reactants, okay? On the right-hand side, that's where our products are. That's always the orientation that we have, where we move left to right. That's, our convention. We have energy over here. Sometimes it will be called potential energy. Later on, we'll talk about Gibbs free energy. It's just some measure of energy for our system. It doesn't really matter what. Yeah.
Okay, so I know you said the transition state only exists for like an infinitesimally tiny moment.
Yeah.
But would it ever be possible theoretically to get something that's frozen in a transition state?
If you had, there's a transition state, probably. I'm sure that there's certain things we can do to kind of slow them down, right? If we change the molecules that are involved with it. But these are very rare cases, right? If you want to think about it for the other direction, or excuse me, from another perspective, if we slow down the transition state, we're going to be slowing down the entire reaction.
Right.
So practically speaking, there's no real use for that, right?
Wouldn't the molecule be very unstable and manipulable in that state though? Because it's got two partial bonds, but it's missing a solid bond?
Yes. Yeah, that's why, these bonds are made and broken very quickly, right? Things don't want to exist without a bond where they already had a bond, if you want to think about it like that, right? So that's what kind of makes them hard to trap out also. So left and right hand side reactions and products up there in the middle. So at the top of that hill is our transition state. At the top of any hill that you see in one of these diagrams is where a transition state is, okay? So this is just basically riding your bike, right? We start on the left-hand side, we ride our bike up the hill, right? We get to the top. When you're at the top of the hill, what do you want to do?
Code.
Immediately go back down the hill. That's all it is, right? You're not really going to stay up there at the top, right? Which hill is bigger to climb? From the reactants to the products, from the products to the reactants? From the reactants to the products is a bigger hill, okay? So if you imagine you're biking along, right? It's going to take more energy to go up the hill from the reactant side. Got it? And so that's what I was saying on the previous statement there where I said this is endothermic, right? One side's going to be faster than the other. The reverse reaction is quicker than the other. That's all I was saying with this. I'm just visually looking at which hill is higher to climb. The higher the hill, the harder it is to climb. The harder it is to climb, the more energy it takes. The more energy it takes,
The more endothermic.
well, for that step, yes. Yeah. right? If you notice here in the middle, from my reactants to the top of the hill, we have this E sub A. We'll come talk about this again later. This is our activation energy, right? This is the energy to get the reaction to go. Got it? The energy has to come from somewhere. Where's the energy going to come from? Well, maybe we're putting it on the stove and we're heating it up, right? Or maybe we hold a match to it. Or maybe we channel all our inner rage and we yell at the reaction really, really loud, right? We just have to add energy.
Does that ever work?
Well, there are some, what are they called, sonochemical reactions, right? It's just an issue of wavelength right now. So, will be the good question, but I was just kind of making a joke. Don't take it too,
Right, but like,
or
I'm
please,
just,
actually, know what, when next time you guys are in lab,
just start.
with Dr. Tong, just start yelling at your test tubes, right? I would love that, yeah, right?
What's the exact term I can use to blame this on you when I do
Oh,
it?
you can tell him exactly what I said. Yeah, that's fine. He can't
So
fire me.
sono-
He has to teach my class then. He doesn't want to get up at 8 a.m., right?
Sonometric reaction?
Sonochemical.
Sonochemical.
Yeah. So, anyway, right, so we have to add some energy into this to get it to go is what it is, right? Now, well, never mind. I'm not going to make that statement. We'll get to it later. At the end here, the change in energy here is just our analysis of, reactants versus products. Do we have to add net energy into this, or does it gain or release energy, which side we're going here, right? So remember, when we're talking about gaining or releasing energy from a system, we're talking about our enthalpy, we're talking about heat being gained or lost, right? That's one measure of energy that we could have there, right? And that's the kind of stuff that we talked about in Gen Chem 1 with, do we have exothermic or endothermic reactions, right? Our enthalpies of formation, these kind of things that came out of that, right? Cool. Okay, I think we kind of hit everything we needed to on this one there, right? But these are extremely important graphs and ideas. They show us exactly, or not exactly, they show us a lot of the information that we need for a specific reaction is what it is. So we start to see those more and more as we go through more the higher level chemistry classes. Up at the top there, I think we talked about this already too, right? Temperature speeds up every reaction, okay? Temperature speeds up every reaction. Sometimes it's the reactions we want, and sometimes it's the reactions we don't want, right? But but heat is agnostic, right? Temperature, it doesn't say, oh, I only want to, warm up this part over here, right, so to speak, right? So higher temperature, higher average kinetic energy, and then if we have the kinetic energy greater than the activation energy, then this reaction is going to go, right? That's all we're saying about the other two parts. Again, I introduce this here, and we come back and really kind of, actually right now in my organic class, we're talking about this idea right here, and how temperature can affect the different types of products that we can make out of it, right? So if you guys are with me in about a year, then we'll come back to this and say, who taught you Gen Chem? You guys don't remember this, right? And I have myself to blame for it, right? But there it is. All right. So now if we take all that kind of idea here and start to look at some stuff, we can prove it to ourselves if we actually go measure this reaction. At different temperatures, we get different rate constants over there, and we can see that it starts to speed up as we add energy into the system, which makes sense. If you've got a beaker filled with iodide and a beaker filled with that methyl bromide, and you put them together, and you start to add energy to it, right, these things are starting to move around more. And so, if you want to think about it, right, all reactions, to an extent, are a matter of statistics, right? If two things have to find each other in a beaker, and then they have to come together with the right energy, right? If I make them move around more, we increase those odds of that happening. Got it? That's all it's really saying with this, right? They're just moving around more, and then there's a higher chance that they'll find each other, smack together in the right orientation, and a reaction happens. That's kind of the idea there, right?
Wait, I'm slightly confused. The TK on the graph there, that's temperature, right? And so K is inversely proportional to the speed of the reaction?
No. The higher the temperature, the faster the reaction goes, right? So increasing temperature, right, increasing rate.
But over there, it's like when T is big, the K value is small.
2.8 times 10 to the negative 1 is much bigger than 4.8
Oh,
times 10 to the
negative 5, I'm
yeah,
sorry.
Yeah.
I was reading the answer, sorry.
So good? All right, and so we get to probably one of the most important equations that we don't really talk about too much. This is part of my frustration with Gen Chem too. There's all these just core concepts in here that I just get to lightly touch on. And I'm like, okay, we're not going to see it again until 3 years from now, right? So,
Will it
Anyway.
be on the exam?
Hmm?
Will it be on the exam?
Of course, I have to fail you guys somehow, right? This is a great way. It looks very scary again, right? So we have the Arrhenius equation, where we have some constant k is equal to a frequency factor times E to the activation energy over a gas constant times units of temperature. Oh my goodness, okay. So what is this all saying here, right? So this equation has a lot of different applications to it, right? Basically, if we want to simplify this to kind of put it into perspective, we might be able to think about. This is, we can rearrange this Arrhenius equation to calculate the activation energy for a temperature-dependent process. That's all it's saying, okay? The gas constant's a constant, okay? Temperature is easy enough to measure, right? We'll talk, or the frequency is just, well, I don't even know, honestly, now that I think about it. How would we even calculate the frequency factor? I guess we'd have to back it out, given the other constants in there, but we'll show an example of that in a little bit. But the point being here is that we can actually back out the activation energy for a process. Now this is pretty darn important, because if we know the activation energy for something, right, we can kind of optimize the reaction conditions, and we can kind of tweak it and change it a little bit to kind of see how we can make a reaction better, or we can even get information out of how molecules are talking to each other. Right? And what I mean with that is there's applications of this equation to discuss things like viscosity, right? How do molecules flow over each other? There's an energy required for that flow to begin, right? So if you guys have ever, paid attention to the type of oil that you put in your car there, right? You have, 10W, 30, 5W, 40, like all these different numbers that I don't know what the numbers necessarily mean, right? But they represent different viscosities, which is for different engines, and there's a different amount of energy required for these molecules to start to flow past each other, right? So that's kind of some of these important ideas that come out of this stuff, right?
None of them are as good as good old fashioned WD-40 though.
I don't think you should put that into your engine. At least not for the oil is, right? So anyway, now if we take all this, and all we're gonna do is just rearrange this to make our equation into a linear form, right? That's all it is, right? Whenever you see something like this, y equals mx plus b, right? That's all we're talking about here, right? That's all we're trying to do. Why do we need to do that? Well, if we have a linear graph, then we can very easily, right, get an equation from that line, and we can use that to predict what our activation energy, or not activation energy, we can predict the different conditions based off that equation, right? That's all we're trying to say with it. You don't need to know how to get there, right? But the book does kind of use these kind of the linear form of the Arrhenius equation there.
So we'll want to memorize that last line there?
Sure, I mean, if you want to, right?
Well, are we gonna need that knowledge on an exam to know that if we come across?
Yes, go for it, memorize it, there you go. I don't know, I haven't read the exam, right?
It's not comforting.
Okay, I'm sorry. I'm not here to be comforting, I'm here to give information, right? Alright. So what's the point, or what can we do, right? So here's just a typical graph out of, or an Arrhenius type plot is what it is, right? And so the slope is what's important with this. We can back out the slope, and once we have the slope, we can get the activation energy. That's all we're gonna do. Which is actually really darn cool, right? It's really darn cool to be able to back out the activation energy for a process. It's fantastic. Now, I can tell that you guys think it's cool also, because you guys are just stunned to silence, but trust me, it's something that's very important in the realm of chemistry, okay? So, there it is. All right, let's finish up here then, right? I think this is just kind of, did I repeat this stuff? oh, no, I'm sorry, this is the last important part before we get into the last bit here, right? So, for an elementary reaction, right, the rate laws are predictable. That's the important part, okay? We're gonna see why when we come back on Monday, but the idea that for a elementary reaction, their rate laws are going to be predictable, right? A unimolecular reaction is always first order. A bimolecular reaction is always second order, okay? That's the information that we're gonna need to be able to, let's say, even solve the upcoming problems, okay? The idea of unimolecular versus bimolecular and their order that comes with it. Hold on a second, please, right? Complex reactions don't occur as they're written, but we can break them down into the elementary steps. Do you guys catch what I'm saying with this? No matter how complex our reaction is, the mechanisms that we can derive or the mechanisms that we can propose are all just a series of elementary steps. What are elementary steps? They're either unimolecular or bimolecular. And we can express a rate law for those. That's going to be the key part, okay? This right here and the information up there is going to come together to help us to solve the individual rate laws and get rates for complex equations, okay? What's up?
How do we determine if something is unimolecular or bimolecular?
One molecule, two molecules. Unimolecular, bimolecular, right? That's all.
So, if it's unimolecular, there will be one molecule on each side of the reaction.
No, we're talking about the reactants, right? One thing could turn into two, right?
Okay. So if we're starting with one thing, it's unimolecular.
Yep.
If we're starting with two things, it's bimolecular.
Yeah.
Okay, cool, thank you.
All right, cool. So we're done for today. Don't forget the quiz, and we'll pick this back up on Monday then.